The rocket exhaust nobody can explain. On the morning of November 11th, something appeared in the pre-dawn sky that should not exist according to everything we know about how comets behave. A brand new image of 3I Atlas dropped, raw and unfiltered, captured by the Nordic Optical Telescope on La Palma in the Canary Islands. And what it shows is not just unusual, it is physically wrong in ways that make astronomers pause mid-sentence and start their calculations over from scratch. The image reveals a massive jet, a plume of material blasting outward from the nucleus of 3I Atlas, and it is aimed directly at the Sun. Not away from it, toward it. If you have followed this object since July, you know this is not the first time we have seen this sunward jet, this anti-tail that defies the basic physics of cometary behaviour. But seeing it again, post-perihelion, after the object swung around the Sun and survived, changes everything about what this means. Before we go further, I need you to do something for me. If you are enjoying this deep dive into the latest 3I Atlas developments, hit that like button and subscribe to the channel. Both of those actions help more than you might think. And here is something I am genuinely curious about. Tell me in the comments where you are listening from right now, what time it is there, and what your gut reaction is to these sunward jets. Do you think we are looking at extreme comet physics, or something else entirely? I read every comment, and your perspectives always add something valuable to these conversations. Now, back to November 11th. The Nordic Optical Telescope, with its 2.56 metre primary mirror, locked onto 3I Atlas as it sat 1.43 astronomical units from the Sun and 2.16 astronomical units from Earth. The image region spans roughly 500,000 kilometres, an enormous field of view necessary to capture the scale of what is happening around this object. What the data revealed was a prominent elongation in the glow surrounding 3I Atlas, projecting to a position angle of 106 degrees, give or take 10. The projected sunward direction from the object at that time was 115 degrees. Those numbers are close, very close, close enough that we are not talking about a geometric illusion or a trick of perspective. This is the same phenomenon Hubble caught back on July 21st. The Space Telescope observed 3I Atlas and documented an anti-tail, a structure of material pointing toward the Sun, instead of being pushed away by solar radiation pressure and the solar wind like every normal comet tail in the solar system. That July image was analysed, debated, and eventually filed away by some researchers as an unusual but potentially explainable quirk. But now, months later, after perihelion, the anti-tail is back. Same geometry, different telescope, different observing team, same result. The image also shows a weaker asymmetry at a position angle of 301 degrees within 1 degree of precision. That aligns almost perfectly with the projected anti-solar direction of 295 degrees. So we have two jets, one pointing at the Sun, one pointing away, and both are visible in the same frame. This is not chaos, this is structure. This is repeatability, and repeatability in science is the thing that separates noise from signal. David Jewett and Jane Liu, the astronomers who captured this data, have been studying comets and distant solar system objects for decades. These are not amateur skywatchers stumbling onto something strange. These are professionals with access to world-class instruments, and they are reporting something that does not fit the standard model. The long-range jet structures that have been evident in recent wide-field images, those enormous plumes stretching millions of kilometres into space, are not visible in this Nordic Optical Telescope data. That absence is likely because the observations were taken through an R-band filter, which excludes most of the gaseous emission lines that make those jets light up in other wavelengths. So what we are seeing here is the dust and the densest material, the stuff that does not simply vanish when you filter out the gas emissions. Which brings us to the problem, the truly uncomfortable problem that no one has a clean answer for yet. Given the scale of the jets that have been reported in recent days, the fact that 3I Atlas remains a single body is surprising if this is a natural comet. Let me restate that it is not just surprising, it is anomalous. On November 9th, just 2 days before this Nordic image, another set of wide-field observations captured 3I Atlas displaying jets that reach out to roughly 1 million kilometres toward the Sun and roughly 3 million kilometres in the opposite direction. 3 million kilometres, that is nearly 8 times the distance from the Earth to the Moon. That is not a puff of gas, that is a sustained, massive outflow of material. For a natural comet, the outflow velocity of jets is expected to be around 0.4 kilometers per second. That speed is roughly the sound speed of gas at the distance 3I Atlas currently occupies from the Sun. At that velocity, for the jets to extend as far as they do, they would need to have been actively flowing for a timescale of 1 to 3 months. That means these jets are not transient. They are not brief bursts. They are sustained structures that have persisted through some of the most intense solar heating this object has experienced. Now here is where the math becomes uncomfortable. The jets directed toward the Sun are being stopped by the solar wind at a distance of about 1 million kilometers from 3I Atlas. The solar wind at this location is moving at roughly 400 kilometers per second, 1,000 times faster than the expected outflow speed of a natural comet. For the jets to maintain their structure and not be instantly shredded by that solar wind, they need to have a significantly higher mass density than the surrounding space. The calculations suggest a mass density of a few million proton masses per cubic centimetre at that 1 million kilometre mark. When you multiply that density by the outflow speed and scale it over the area of the jet, you get a mass flux of approximately 5 billion tonnes per month per area of a million kilometres on a side. 5 billion tonnes per month. Let that settle for a moment. That is the amount of material 3I Atlas would need to be ejecting to sustain these jets under natural comet physics. To put that in perspective, that is roughly the mass of a small mountain being hurled into space every 30 days. And this is not a one-time event. This is continuous output over the course of months. So where is that energy coming from? For a comet, the energy source is solar radiation. Sunlight heats the surface, sublimates the ices, and the expanding gas carries dust and larger particles away from the nucleus. The sublimation of carbon dioxide ice requires 600 joules per gram. If 3I Atlas is ejecting 5 billion tonnes of carbon dioxide over a 1-month period near perihelion, it must absorb at least 3 times 10 to the 18th joules of energy. At the perihelion distance of 3I Atlas, the Sun provides about 700 joules per square metre per second. To absorb enough energy to sublimate that much carbon dioxide, the object would need an absorbing surface area larger than 1,600 square kilometres. That is the area of a sphere with a diameter of roughly 23 kilometres, but Hubble measured 3I Atlas at a maximum diameter of 5.6 kilometres. The numbers do not match. They are off by a factor of 4. If the ice is water instead of carbon dioxide, the situation gets worse. Water ice requires more energy to sublimate, which means the required diameter jumps to 51 kilometres. Hubble saw an object that is 5.6 kilometres across, not 51. The discrepancy is not small, it is enormous. On natural cometary nuclei, ice does not cover the entire surface uniformly. Pockets of volatile material are often buried beneath layers of dust and rock, and only a fraction of the total surface area actively sublimates at any given time. That makes the numbers even more untenable. If only a small fraction of the surface is actively venting gas, then the effective area available for absorbing solar energy shrinks further, and the required size of the object grows even larger to compensate. There is no reasonable configuration of a natural comet nucleus that reconciles these observations with the known physics of cometary outgassing. And yet 3I Atlas did not break apart. It did not fracture into a debris field. It did not disintegrate into fragments. It remains, as of November 11th, a single intact body. Comets that lose significant fractions of their mass in short periods of time tend to come apart. The internal structure weakens, thermal stresses build up, and eventually the nucleus fractures. We have seen this happen with other comets that passed close to the Sun. They brighten dramatically, they flare, and then they shatter. 3I Atlas brightened, it flared, and it stayed together. That structural integrity is itself an anomaly. If this object is losing mass at the rates implied by the jet observations, and if that mass loss is distributed unevenly across the surface as the jets suggest, then the mechanical stresses on the nucleus should be immense. Natural cometary nuclei are not solid monolithic rocks. They are loosely bound aggregates of ice, dust, and rock, sometimes described as dirty snowballs or icy rubble piles. They do not have the tensile strength to withstand the kind of asymmetric outgassing we are seeing here without coming apart. Unless the object is not a loosely bound rubble pile, unless it has structural integrity that exceeds be it what we expect from a natural comet, unless it is something else. Let me be very clear about what I'm not saying. I am not saying we have proof of anything extraordinary yet. What I am saying is that the data we have, the observations that are now on the record from multiple independent teams using different instruments, do not fit comfortably into the natural comet model. Every attempt to make the numbers work requires assumptions that stretch the boundaries of what we know about cometary physics. Every calculation ends with a caveat, a footnote, an acknowledgement that something here does not add up. The image from November 11th is just one data point, but it is a data point that confirms what we saw in July and what we have been seeing in the weeks since perihelion. The sunward jet is real, it is persistent, and it is behaving in ways that challenge our understanding. The fact that the object remains intact after losing what should be a catastrophic amount of mass is another piece of the puzzle that does not fit easily into place. There is an alternative explanation, one that requires far less hand-waving and far fewer implausible assumptions. If the jets are not produced by solar heating and ice sublimation, if they are instead produced by some form of active propulsion, then the required mass loss drops dramatically. Chemical rockets expel exhaust at velocities of 3 to 5 kilometers per second, 10 times faster than the natural outflow speed of cometary gas. Ion thrusters reach even higher speeds, 10 to 50 kilometers per second. At those velocities, the amount of propellant needed to produce the observed jet shrinks by 1 to 2 orders of magnitude. Suddenly, instead of requiring the object to lose half its mass, you only need a small percentage, perhaps less than 1%, to be fuel. This is not science fiction, this is engineering. Human spacecraft use chemical and ion propulsion all the time. We understand the physics, we understand the efficiency, and we understand the exhaust velocities. If 3I Atlas were using similar technology, even technology only marginally more advanced than our own, the observations would make sense. The jets would make sense, the structural integrity would make sense, and the energy budget would make sense. But that explanation requires us to accept that 3I Atlas is not natural. It requires us to consider that we are looking at a technological object, an artifact from another civilization, something that was designed and built and sent on a trajectory through interstellar space for purposes we can only guess at. That is a massive claim, and massive claims require massive evidence. We do not have that evidence yet. Not conclusively, but we have anomalies, lots of them, and those anomalies are piling up. The November 11th image is not the end of this story, it is the beginning of the next chapter. Starting today, Earth-based observatories can focus on 3I Atlas again as its angular separation from the Sun grows beyond 30 degrees. That means clear observational windows, longer exposure times, and the ability to track the object continuously over the coming weeks. Spectroscopic observations are planned, measurements that will tell us the velocity of the gas in the jets, the composition of that gas, and the mass flux in real time. Those observations will either confirm that this is an extremely unusual but ultimately natural comet, or they will deepen the mystery further. On December 19th, 3I Atlas will make its closest approach to Earth, coming within 269 million kilometers of our planet. That is still far away, but it is close enough for the Hubble Space Telescope and the James Webb Space Telescope to obtain high-resolution data. It is close enough for ground-based observatories to measure rotation rates, search for surface features, and characterize the jets in exquisite detail. If there are fragments, if the object did break apart near perihelion, and we are seeing the aftermath, we will know by then. If it remains a single body, if it continues to display these anti-tails and these impossible jets, we will know that too. The data is coming, the observations are planned, and the answers are within reach. What we do with those answers, how we interpret them, and whether we are willing to follow the evidence wherever it leads, that is up to us. Science works best when we remain open to possibilities, even uncomfortable ones, and when we let the data speak for itself, rather than forcing it into preconceived categories. 3I Atlas has already shown us that it does not behave like other comets. It has survived perihelion intact, it continues to display jets that point in directions they should not, and it has done all of this while maintaining a level of structural integrity that defies the standard model. The November 11th image from the Nordic Optical Telescope is just the latest confirmation that whatever this object is, it is not following the script we wrote for it. And that, more than anything else, is what makes this moment so compelling. We are watching something unfold in real time, something that challenges assumptions and forces us to ask questions we did not think we needed to ask. Whether the answer is exotic comet physics or something far stranger, we are living through one of those rare moments in science where the data is ahead of the theory and the universe is showing us something we do not yet fully understand. So keep watching, keep questioning, and keep following the story. Because whatever 3i Atlas turns out to be, it has already earned its place as one of the most fascinating objects to ever pass through our solar system, and we are only just beginning to understand what it has to teach us. NASA's 40-day silence and congressional intervention. While astronomers around the world were capturing ground-based images of 3i Atlas through October and November, there was another set of images that nobody outside NASA had seen, images that were taken over 40 days ago. Images that, according to multiple sources, offer the highest resolution view of this interstellar visitor we have ever obtained. And those images have been locked away, unreleased, caught in what some are calling bureaucratic limbo, and what others are calling something far more deliberate. On October 2nd and 3rd, as 3i Atlas passed within 29 million kilometres of Mars, NASA's Mars Reconnaissance Orbiter turned its HiRISE camera toward the approaching object. HiRISE, the high-resolution imaging science experiment, carries a 50-centimetre aperture telescope specifically designed to capture detailed surface features on Mars. But cameras in space do not care what they are pointed at, and when HiRISE locked onto 3i Atlas, it achieved a spatial resolution of 30 kilometers per pixel. To put that in context, that is roughly 3 times better than the resolution Hubble achieved back in July, when it captured its famous image of the object. 3 times better resolution means 3 times more detail. It means the ability to resolve structures on or around the nucleus that were simply invisible in previous observations. It means the potential to see whether the jets are emanating from discrete points on the surface or from a more distributed area. It means the difference between guessing at the geometry of this object and actually measuring it. And yet, as of today, those images have not been released to the scientific community or to the public. The official explanation from NASA initially centered on the United States government shutdown, which began on October 1st, just one day before the HiRISE observations were taken. During a government shutdown, many federal agencies operate on reduced staff and non-essential activities are postponed until normal operations resume. Scientific data releases, particularly those that require calibration, processing and review, can fall into that category of postponed activities. On the surface, the explanation makes sense. The government was shut down, NASA was operating with limited personnel, and the data release was delayed. But then people started asking questions. If the shutdown was the reason for the delay, why were other Mars images being released during the same period? The Mars Reconnaissance Orbiter continued to transmit data, and other images from the HiRISE camera were processed and made publicly available through NASA's standard data archives. It was specifically the 3i Atlas images that remained unreleased. That inconsistency did not go unnoticed. Harvard astrophysicist Avi Loeb was among the first to publicly call attention to the delay. In a series of blog posts and media interviews, including a high-profile appearance on the Joe Rogan podcast, Loeb argued that the HiRISE images represented time-sensitive scientific data that should not be held hostage to bureaucratic delays. He pointed out that astronomers were actively planning follow-up observations of 3i Atlas, and that having access to the highest resolution imagery available would significantly improve the quality and focus of those observations. Every day of delay meant missed opportunities to coordinate ground-based telescopes with the spacecraft data, to refine models of the object's behaviour, and to answer fundamental questions about its nature. Loeb went further. In one essay, he suggested that the delay was probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity. It was a pointed comment, designed to highlight what he saw as an absurd situation where scientific progress was being impeded by administrative inertia. He also noted that conspiracy theorists had begun speculating that the delay might be intentional, that perhaps the images showed something NASA did not want the public to see. Loeb dismissed that conspiracy angle, but he acknowledged that the longer the delay continued, the more fuel it provided to those who believed in cover-ups and hidden agendas. Then Congresswoman Anna Paulina Luna entered the picture. Luna, a Republican representative from Florida, has previously been involved in efforts to increase transparency around unidentified aerial phenomena and potential non-human intelligence. She has publicly supported scientific inquiry into anomalous objects and has advocated for the release of government-held data that could advance our understanding of these phenomena. When she learned about the unreleased high-res images of 3I Atlas, she saw it as another case where important scientific information was being withheld without adequate justification. On November 6th, Luna sent a formal letter to Sean Duffy, NASA's acting administrator. In that letter, she specifically requested the release of images captured by the HiRISE camera aboard the Mars Reconnaissance Orbiter between October the 2nd and 3rd. She also asked for supplementary data from the Perseverance rover and any other Mars missions that may have detected unusual activity near Mars around or after October 3rd, when 3I Atlas passed within approximately 30 million kilometers of the planet. Luna framed her request in terms of scientific importance and public interest, arguing that the data could provide crucial insights into the composition, trajectory, and possible interaction of 3I Atlas with the solar environment. Luna's letter was not a casual inquiry. It was an official communication from a member of Congress to a federal agency, the kind of communication that carries weight and demands a response. And it worked. Within days of the letter being sent, Luna's office announced that NASA had agreed to provide a formal briefing for the Congresswoman and her staff regarding 3I Atlas and the status of the high-rise images. The fact that it took a congressional intervention to prompt this response is significant. It suggests that the standard channels for scientific data access were not functioning as they should, or that there was some internal reluctance within NASA to release the images without external pressure. Either way, the involvement of an elected representative shifted the dynamic. This was no longer just a dispute between scientists and bureaucrats, it was a matter of congressional oversight and government accountability. Social media amplified the story in unexpected ways. Kim Kardashian, the businesswoman and media personality, posted on X asking Sean Duffy to spill the tea on 3I Atlas. Duffy responded publicly, stating that NASA's observations show this is the third interstellar comet to pass through our solar system, with no aliens and no threat to life on Earth. It was a reassuring message, the kind of statement designed to calm public concerns and dismiss the more sensational interpretations of the object. But Loeb criticized that response. He pointed out that Duffy had taken the time to reply to a celebrity inquiry on social media, while ignoring formal requests from scientists for the release of data. Loeb titled one of his follow-up essays, "Kim Kardashian is welcome to join my research team on 3I Atlas," a tongue-in-cheek jab at the priorities NASA seemed to be displaying. The subtext was clear. If you want NASA to pay attention to scientific concerns, maybe you need a few million social media followers. The government shutdown officially ended, and still the images did not appear. Luna tweeted that she had a good conversation with NASA, and that as soon as the government reopened, they would be releasing the images and data. She added that due to bureaucratic reasons, they could not release the material until then. That statement provided some clarity but also raised more questions. If the shutdown was truly the only barrier, why had NASA not immediately released the images once normal operations resumed? What bureaucratic reasons were still preventing the data from being made public? Meanwhile, China's space agency stepped into the information gap. The China National Space Administration released images of 3I Atlas captured on October the 3rd by the Tianwen-1 Mars orbiter. Tianwen-1 carries a high-resolution imaging camera with a 38.7 cm primary mirror, slightly smaller than HiRISE, but still capable of impressive resolution. The Chinese images showed the nucleus of 3I Atlas surrounded by a coma with a diameter of several thousand kilometers. CNSA researchers even generated an animation of the trajectory of 3I Atlas across the Martian sky, based on a series of 30-second exposures. The Chinese release was significant for two reasons. First, it demonstrated that other space agencies were willing and able to release their 3I Atlas observations without lengthy delays. Second, it provided the scientific community with at least some high-resolution data from the Mars flyby, even if it was not quite as detailed as the NASA HiRISE imagery. But it also highlighted the contrast between how different agencies handled the same event. China released their data within weeks. NASA, as of mid-November, still had not. Loeb praised the Chinese release and used it to further emphasize the need for NASA to follow suit. He wrote that while the heroic images from Tianwen-1 were valuable, the high-rise images from NASA's Mars Reconnaissance Orbiter would offer superior resolution and a different viewing geometry that could provide complementary information. Both datasets together would give scientists a much more complete picture of 3I Atlas during its close approach to Mars. The delay also had practical consequences for observational planning. Ground-based telescopes have limited time to observe any given object, and scheduling those observations requires advanced planning, proposals, and coordination among multiple institutions. High-resolution images from Mars could have informed decisions about which wavelengths to prioritize, which specific features to focus on, and how to allocate precious telescope time most effectively. Every week of delay meant that some of those opportunities were lost. By early November, the frustration within the scientific community was palpable. Social media posts from astronomers and planetary scientists echoed Loeb's concerns, with many expressing disbelief that such important data could be held up for so long over what appeared to be administrative rather than technical issues. Some pointed out that NASA has a long-standing policy of making mission data publicly available, and that the high-rise archive is normally updated on a regular schedule with minimal delay. The 3I Atlas images were an outlier, an exception to the standard process, and no one seemed to have a satisfactory explanation for why. Then came the November 11th observation from the Nordic Optical Telescope showing that 3I Atlas had survived perihelion intact. That observation made the unreleased high-rise images even more important. If NASA's Mars orbiter had captured the object just before perihelion, and ground-based telescopes were now seeing it after perihelion, comparing those two datasets could reveal whether the object had changed in any measurable way. Had it lost mass? Had its jet activity increased or decreased? Were there signs of fragmentation that had since dispersed? These were answerable questions, but only if the data was available. Luna's office confirmed that NASA had officially responded and agreed to the briefing, but a date had not yet been set. The fact that the agency was now formally accountable to Congress signaled a shift. This was no longer a quiet internal matter that could be managed through normal channels. It had become a public issue with elected officials involved, and that meant NASA would need to provide answers, not just to scientists, but to representatives of the American people. The entire episode raises uncomfortable questions about transparency, priorities, and the mechanisms by which scientific data is shared. NASA operates on public funding, and the Mars Reconnaissance Orbiter was built and launched with taxpayer money. The data it collects belongs, in a sense, to everyone. When that data is withheld for reasons that are unclear or appear inconsistent, it erodes trust. It feeds speculation. And it creates precisely the kind of information vacuum that conspiracy theories thrive in. As of now, the high-rise images remain unreleased. The briefing with Congresswoman Luna has been promised but not yet scheduled, and 3I Atlas continues its journey through the inner solar system, moving closer to Earth with each passing day. December 19th is approaching, and with it comes the opportunity for even better observations from Earth-based and space-based telescopes. But the Mars flyby data, that unique perspective from a spacecraft that was in the right place at the right time, remains locked away. Science should not require congressional intervention to function. Data should flow through established channels, reviewed and released according to transparent policies. The fact that we are still waiting for images taken in early October tells a story about how systems can fail even when everyone involved believes they are following the rules. And in this case, that failure has real consequences for our ability to understand one of the most intriguing objects to visit our solar system in decades. The object that refused to die. There was a very real expectation, shared by multiple astronomers in the weeks leading up to perihelion, that 3I Atlas might not survive its closest approach to the Sun. The math suggested it, the YIS, mass loss calculations pointed toward it, and the history of comets that had ventured this close to our star seemed to confirm it. Comets break apart. They fracture under thermal stress. They shed material at unsustainable rates, and when they lose too much mass too quickly, their internal structure fails. It happens all the time. It should have happened here. It did not. The November 11th images from the Nordic Optical Telescope were not just remarkable because they showed the sunward jets we have been discussing. They were remarkable because they showed a single intact nucleus. No fragmentation, no debris field, no sign that this object had torn itself apart under the extreme conditions it experienced during its swing around the Sun. 3I Atlas went into perihelion as one object, and it came out as one object. That simple fact, that basic observation, is profoundly difficult to reconcile with the natural comet hypothesis. Let me walk you through why this survival is so unexpected. We have already covered the mass loss rates implied by the jet observations, the 5 billion tons per month figure that represents the kind of outflow necessary to sustain jets extending millions of kilometers into space. Losing that much mass is not a gentle process. When a comet sheds material on that scale, it is not like a slow leak. It is more like an explosion in slow motion. The forces involved are enormous. The pressure gradients are steep, and the structural integrity of the nucleus is tested in ways that most natural bodies simply cannot withstand. Natural cometary nuclei are not solid rocks. They are aggregates, collections of ice, dust, and rocky material that are loosely bound together by their own weak gravity and by the frozen ices that act as a kind of glue. When sunlight heats the surface and sublimates those ices, the glue melts. The material that was holding everything together turns into gas and escapes. What is left behind is a weakened structure, and if the heating is intense enough and the mass loss rapid enough, that structure fails. We have observed this failure mode in other comets. Comet Shoemaker-Levy 9 famously broke apart into more than 20 fragments before it collided with Jupiter in 1994. Comet Linear disintegrated in the year 2000 as it approached the Sun, shattering into dozens of pieces that were tracked by telescopes around the world. Comet Isen, which was expected to put on a spectacular show in 2013, broke apart during its perihelion passage and essentially vaporized, leaving behind only a faint cloud of dust. The list goes on. Comets are fragile, and perihelion is where that fragility is most often exposed. 3I Atlas reached perihelion on October the 29th. At that point, it was approximately 203 million kilometers from the Sun, closer than the orbit of Mars, but still well outside the orbit of Earth. By cometary standards, this was not an extreme. Perihelion. It was not grazing the solar corona. It was not diving into the inner solar system where temperatures reach thousands of degrees. And yet, the object brightened dramatically. Data from space-based observatories like SOHO and Stereo showed 3I Atlas flaring to magnitude 7 or 8, several magnitudes brighter than its pre-perihelion brightness. That kind of brightening indicates intense activity, massive outgassing, and exactly the kind of conditions that lead to structural failure. But when the object emerged from behind the Sun and became observable again from Earth in early November, it was still intact. The first post-perihelion images showed jets, they showed a coma, they showed all the hallmarks of ongoing cometary activity. What they did not show was fragmentation. There were no multiple nuclei, no spreading debris field, no indication that this object had come apart. The Nordic Optical Telescope data confirmed it. David Jewett and Jane Liu specifically noted in their report that there was no evidence for breakup following the perihelion passage. They were looking for it. The scientific community was expecting it, and it was not there. One object in, one object out. Now, let me introduce another layer to this puzzle. On November 8th, just days before the Nordic Optical Telescope observations, a team of astronomers including Michael Jaeger, Gerald Riemann, and Enrico Prosperi captured images of 3I Atlas that showed at least 7 distinct jets emanating from the nucleus. 7 separate streams of material pointing in different directions, creating a complex geometry that looked less like a comet and more like something with multiple exhaust ports. Those images were taken when 3I Atlas was 29 degrees from the Sun in the sky, high enough above the horizon to get clear observations but still close enough to the Sun that twilight interference was a factor. 7 jets, all active simultaneously, all pushing material outward from a central body. If you're trying to model this as a natural comet, you need to explain how a 5.6 kilometer diameter object the size measured by Hubble can sustain 7 distinct outgassing regions without tearing itself apart. Each jet represents a location on the surface where volatiles are being heated and sublimated, where gas is expanding and escaping, and where the local structure is under intense stress. Having 7 of these active zones distributed across a relatively small nucleus means the object is being pushed and pulled in multiple directions at once. Imagine inflating a balloon, but instead of inflating it evenly, you're inflating it from 7 different points, each with its own internal pressure source. The balloon would not hold its shape. It would bulge, distort, and eventually rupture. Cometary nuclei are not as strong as rubber balloons. They are weaker, more porous, more prone to fracturing, and yet 3I Atlas is holding together. The sunward jets add another dimension to this problem. Normal cometary jets are pushed away from the sun by solar radiation pressure and the solar wind. They follow predictable paths and their dynamics are well understood. Sunward jets, jets that point back toward the sun, require a different explanation. One possibility is that the gas is being ejected with enough velocity to overcome the radiation pressure, at least initially, before the solar wind eventually stops it and turns it around. But that requires even higher outflow velocities, which in turn requires even more energy, which brings us back to the same problem of where all that energy is coming from if this is just solar heating. Another possibility is that the jets are not purely radial outflows. Perhaps they are being deflected by the rotation of the nucleus, or by local topography, or by interactions between different gas streams. These are plausible mechanisms, and they could potentially explain some of what we are seeing, but they do not explain why the object survives the process. Deflected jets still represent mass loss. They still exert forces on the nucleus, and they still require the structural integrity to withstand those forces without fragmenting. Avi Loeb has argued that if 3I Atlas were a natural comet experiencing this level of mass loss, it should have broken into at least 16 equal pieces, and likely many more. That calculation is based on the energy budget, the required surface area for sublimation, and the comparison with the measured size of the nucleus. If you cannot fit enough sublimating surface area onto a single 5.6 kilometer object, then you need more surface area, which means more fragments. The fact that we are not seeing those fragments means either the calculations are wrong, or the object is not behaving like a natural comet. Let me be clear about what we are not seeing. We are not seeing a debris cloud. We are not seeing a trail of fragments strung out along the orbit. We are not seeing the kind of dispersed material that typically results from cometary breakup. When comet linear disintegrated, observers tracked individual fragments as they separated and drifted apart. When Eason broke apart, there was a visible transition from a compact nucleus to a diffuse cloud. None of that is happening with 3I Atlas. The November 9th wide-field images captured by Frank Niebling and Michael Buckner provide additional context. Those images, taken with 2 telescopes combining multiple exposures, showed the enormous scale of the jet structures, the anti-tail jets extending nearly 1 million kilometers toward the sun and the main tail jet reaching nearly 3 million kilometers in the opposite direction. But crucially, at the center of all that activity, there was a single bright point, the nucleus, unchanged in its apparent structure. If the object had fragmented, we would expect to see that central point resolve into multiple points as the fragments separated. We would expect the jets to become less organized, more chaotic, as material was being ejected from multiple independent sources with different velocities and trajectories. Instead, the jets maintain their structure, they maintain their symmetry, and they all appear to originate from the same compact central region. The implications are unsettling. If 3I Atlas is a natural comet, it is behaving in ways that push the boundaries of cometary physics. It is surviving conditions that should destroy it, it is maintaining structural integrity despite losing enormous amounts of mass, and it is producing jet geometries that are difficult to explain through standard outgassing models. Every observation seems to add another layer of anomaly, another detail that does not quite fit. But if it is not a natural comet, if it is something else, then the survival makes more sense. An artificial structure, something designed and built rather than accreted and frozen, could have the internal framework to withstand these stresses. A spacecraft with a hull with internal compartments with structural reinforcement would not fracture the way a rubble pile would. Thrusters, if that is what we are looking at, would exert forces in controlled directions, and the structure would be designed to handle those forces without coming apart. This is speculative, and I want to emphasize that. We do not have proof that 3I Atlas is artificial. What we have is a growing collection of observations that are difficult to explain if it's natural. The survival through perihelion is one more item on that list, one more data point that challenges the conventional interpretation. There is still the possibility that we are missing something, that there is a natural explanation we have not considered yet, some exotic but ultimately conventional physics that can account for everything we are seeing. comets are complex objects, and our models are based on a limited sample of observations. It is entirely possible that 3I Atlas is simply an outlier, a rare but natural variant that behaves differently from the comets we are more familiar with. Science has to remain open to that possibility, but outliers have explanations. Rare events follow statistical patterns, and when an outlier is this extreme, when it defies expectations in multiple independent ways, at some point you have to consider whether it is actually an outlier or whether it is something categorically different. The line between an extreme natural object and an artificial one is not always clear, but the more anomalies we accumulate, the harder it becomes to stay on the natural side of that line. 3I Atlas refused to die. It went through perihelion, it survived the heating, it endured the mass loss, and it came out the other side intact. That is not what we expected, it is not what the models predicted, and it is not what cometary physics easily accommodates. Whether that survival is the result of us underestimating the resilience of natural comets, or whether it is evidence of something fundamentally different, we do not yet know, but it is a question that demands an answer, and the data to provide that answer is being collected right now. 5 billion tons per month, the impossible math. Numbers do not lie, but they can reveal uncomfortable truths. And the numbers surrounding 3I Atlas, when you sit down and work through them carefully, tell a story that is very difficult to reconcile with what we think we know about comets. This is not about interpretation or philosophical preference, this is about mathematics, thermodynamics, and the laws of physics that govern how objects behave when they interact with sunlight and the solar wind. So let me walk you through the calculation that has been keeping scientists up at night. We start with the jets. The wide field observations from early November show material extending roughly 1 million kilometers toward the Sun and roughly 3 million kilometers in the opposite direction. These are not theoretical numbers. They are measured angular sizes, converted to physical distances based on the known distance of 3I Atlas from Earth. 1 million kilometers is about 2.6 times the distance from the Earth to the Moon. 3 million kilometers is nearly 8 times that distance. We are talking about structures that span a significant fraction of the space between Earth and the Sun. For a natural comet, material in these jets is being pushed outward by the expanding gas that results from solar heating. The velocity of that expansion is determined by the temperature of the gas, which in turn is determined by how much solar energy the surface is absorbing. At the current distance of 3I Atlas from the Sun, roughly 1.4 astronomical units, the expected outflow velocity is about 0.4 kilometers per second. That is not a guess. It is a calculation based on the temperature of gas in thermal equilibrium with sunlight at that distance. It is the sound speed in the gas, the characteristic velocity at which pressure waves propagate through the material. 0.4 kilometers per second is not fast. For comparison, the escape velocity from Earth's surface is 11.2 kilometers per second. The solar wind at this distance from the Sun moves at about 400 kilometers per second, 1,000 times faster than the cometary outflow. But even at 0.4 kilometers per second, material can travel substantial distances given enough time. To reach 1 million kilometers at that speed takes approximately 29 days. To reach 3 million kilometers takes about 87 days, just under 3 months. So the jets we are observing now must have been actively flowing for 1 to 3 months. They are not the result of a brief outburst. They are sustained structures that have persisted through perihelion and into the post-perihelion period. That duration matters because it sets the timescale over which mass loss has been occurring. Now let us think about the solar wind. The jets pointing toward the Sun are being stopped at a distance of roughly 1 million kilometers from the nucleus. We know they are being stopped because we can see where the jets end. We can see the boundary where the outflowing material from 3I Atlas meets the incoming solar wind and gets turned around. That boundary is not arbitrary. It is determined by a balance of forces. The ram pressure from the solar wind, the momentum carried by those fast-moving particles, has to be matched by the ram pressure from the cometary jets, the momentum carried by the much slower but much denser material coming from 3I Atlas. Ram pressure is density times velocity squared. The solar wind at this location has a density of a few protons per cubic centimeter and a velocity of about 400 kilometers per second. That gives it a certain ram pressure. For the cometary material to stand up against that pressure, it needs either much higher velocity or much higher density. Since we have already established that the velocity is only about 0.4 kilometers per second, 1,000 times slower than the solar wind, the density has to be about 1 million times higher. The numbers force that conclusion. To stop the solar wind at a distance of 1 million kilometers, the mass density of the jets at that location must be a few million proton masses per cubic centimeter. Now we can calculate mass flux. Mass flux is the rate at which mass is flowing through a given area. It is density times velocity times area. We have the density, we have the velocity, and we can estimate the area based on the observed cross-section of the jets. When you multiply those numbers together, you get approximately 5 billion tons per month flowing through an area, 1 million kilometers on a side, 5 billion tons per month. Let me give you some context for that number. Mount Everest, the tallest mountain on Earth, has a mass of roughly 810 billion tons. So 3I Atlas, if this calculation is correct, is ejecting the equivalent of about 1/600th of Mount Everest every month. That is an enormous amount of material for an object that Hubble measured at 5.6 kilometers across. But the real problem is not just the amount of mass being lost. It is where the energy to drive that mass loss is coming from. To turn ice into gas requires energy, a specific amount of energy per gram of material depending on what kind of ice we are talking about. For carbon dioxide, which is one of the main constituents detected in the coma of 3I Atlas, the energy required is 600 joules per gram. To sublimate 5 billion tons of carbon dioxide in 1 month requires 3 times 10 to the 18th joules. Where does that energy come from? In a natural comet. It comes from the sun. Sunlight hits the surface heats up, and the heat conducts inward to sublimate the subsurface ices. At the perihelion distance of 3I Atlas, the sun devours about 700 joules per square meter per second. That is the solar constant at that distance, the amount of energy falling on each square meter of surface every second. If we need 3 times 10 to the 18th joules over the course of a month, and the sun is providing 700 joules per square meter per second, we can calculate how much surface area is needed to absorb that much energy. The answer is more than 1,600 square kilometers. That is the surface area of a sphere with a diameter of about 23 kilometers. Hubble measured 3I Atlas at 5.6 kilometers. The area of a sphere with a diameter of 5.6 kilometers is about 98 square kilometers. We need 1,600, we have 98. The discrepancy is more than a factor of 16. You might argue that the object is not a perfect sphere, that it could be elongated or irregularly shaped in a way that increases its effective surface area. Fair point, but even if you assume the most favourable geometry, even if you stretch the object into a long thin cylinder or a flat disk to maximise the area exposed to sunlight, you cannot make up a factor of 16 without violating the size constraint that Hubble measured. The object simply is not big enough to absorb the energy needed to drive this level of mass loss through natural solar heating. And that is assuming carbon dioxide, which is relatively easy to sublimate. If we are talking about water ice instead, the situation gets worse. Water requires more energy to sublimate, about 2,800 joules per gram compared to 600 for carbon dioxide. That increases the required surface area by another factor of 4.7, bringing the needed diameter to about 51 kilometers. Hubble measured 5.6. The gap is now a factor of more than 80. You might also argue that the ices on a comet are not uniformly distributed, that they exist in pockets or layers beneath a dusty surface, and that only certain active areas are actually sublimating at any given time. That is true for many comets, but if only a fraction of the surface is active, then the problem gets worse, not better. If only 10% of the surface is actually sublimating ice, then you need 10 times more total surface area to deliver the same energy to those active regions. The math does not help you here. It works against you. There is another way to look at this problem, and it comes from the total mass of 3I Atlas itself. Based on the lack of non-gravitational acceleration prior to perihelion, and using reasonable assumptions about the density of cometary material, Loeb has estimated the total mass of 3I Atlas at approximately 33 billion tons. If the object is losing 5 billion tons per month, that is about 15% of its total mass. Losing 15% of your mass in a month is catastrophic for a loosely bound object. It is more than enough to trigger fragmentation, and yet we have already discussed how the object remains intact. But let us take this even further. The jets are not just active for 1 month. The observations suggest they have been flowing for 1 to 3 months. If we take the upper end of that estimate, 3 months, then the total mass loss is 15 billion tons, nearly half the estimated total mass of the object. At that point, you're not looking at a comet that is venting some of its volatiles, you are looking at an object that is disassembling itself. And yet there it is, still in one piece. So what are the ways out of this mathematical trap? One option is that our estimate of the mass flux is wrong. Perhaps the jets are less dense than we think, or perhaps the velocity is higher than we think, which would reduce the required density to balance the solar wind. But both of those parameters are constrained by observations and by physics. The velocity is tied to the temperature, which is tied to the solar flux. The density is tied to where the jets stop, which we can see. There is not much room to adjust those numbers without breaking something else. Another option is that the energy is not coming from solar heating alone. Perhaps there is an internal heat source, something left over from the formation of the object or generated by radioactive decay or tidal stresses. But 3I Atlas is not close enough to the Sun for tidal heating to be significant, and radioactive decay is far too weak to supply the needed energy on these timescales. You would need something much more energetic, and at that point you are no longer talking about a natural process. A third option is that the mass loss is being grossly overestimated, that the jets are somehow much less massive than the calculations suggest, and that we are being fooled by some optical effect or measurement error. This is always possible, and it is important to remain skeptical of any single line of evidence. But the observations of the jets come from multiple independent teams using different instruments. The Nordic Optical Telescope saw them, the Wide Field Imagers saw them, and the overall geometry is consistent across all the datasets. If the jets are an illusion, it is a very convincing and very consistent illusion. The fourth option, the one that Loeb and others have been cautiously suggesting, is that the jets are not driven by natural outgassing at all. If they are the result of active propulsion, if they are exhaust from some kind of thruster system, then the energy budget looks completely different. Chemical rockets expel exhaust at velocities of 3 to 5 kilometers per second, 10 times faster than natural cometary outflow. Ion thrusters reach 10 to 50 kilometers per second. At those velocities, the required mass flux to produce the observed jets drops by 1 to 2 orders of magnitude. Instead of needing to eject 15% of the object's mass, you might only need 1% or less. That is still a significant amount of propellant, but it is within the realm of what an engineered system could carry. Human spacecraft routinely carry fuel loads that represent a substantial fraction of their total mass, and they use that fuel to perform maneuvers and change orbits. If 3I Atlas were using similar technology, even technology only marginally better than our own, the observations would make sense. The energy would be stored chemically or electrically rather than coming from sunlight, and the mass loss would be deliberate rather than passive. This is the point where the mathematics pushes you toward a conclusion that many scientists are uncomfortable with, not because the conclusion is impossible, but because it is extraordinary, and extraordinary claims require extraordinary evidence. The numbers alone do not prove that 3I Atlas is artificial. What they prove is that the natural explanation requires assumptions that are increasingly difficult to justify. The object is either much larger than Hubble measured, or much less massive than dynamics suggest, or losing far less mass than the jets imply, or being driven by an energy source we have not identified. Each of those possibilities requires us to set aside some piece of observational evidence or some physical constraint. Or the object is not natural, and if it is not natural, then the mathematics work. The survival works, the jets work. Everything fits, as long as you are willing to accept that we might be looking at technology rather than geology. The numbers do not lie, they point towards something that does not fit the standard model. Whether that something is exotic natural physics or actual artificial construction, the data will eventually tell us. But right now, the mathematics are screaming that this object is not behaving the way a comet should. And that gap between expectation and observation is what makes 3I Atlas one of the most compelling mysteries in modern astronomy. Chemical rockets versus comet physics. Let me take you inside a thought experiment, one that requires setting aside assumptions and looking at the problem from first principles. Forget for a moment what you think 3I Atlas should be. Instead, let us compare two different systems, two different ways of producing the jets we are observing, and see which one fits the data better. On one side we have natural cometary outgassing driven by solar heating. On the other side we have active propulsion systems, the kind humans have been building and flying for decades. This is not about belief or speculation, this is about engineering and physics. A natural comet loses mass through sublimation. Sunlight heats the surface, frozen volatiles turn directly from solid to gas without passing through a liquid phase, and that expanding gas carries dust and larger particles away from the nucleus. The process is passive, it happens automatically when a comet gets close enough to the Sun, and the rate of mass loss is determined by how much solar energy the surface can absorb and how efficiently that energy is transferred to the subsurface ices. The exhaust velocity from this process is limited by thermodynamics. When a gas expands from a solid surface, its velocity is determined by the temperature of that gas. At the distances we are talking about, roughly 1 to 1.4 astronomical units from the Sun, the surface temperature of a comet reaches a few hundred degrees Kelvin. At those temperatures, the thermal velocity of molecules, the speed at which individual gas molecules are moving due to their random thermal motion, is a few hundred meters per second. The bulk outflow velocity, the organized flow of gas away from the surface, ends up being around that same value, typically 0.3 to 0.5 kilometers per second. That velocity is fixed by physics. You cannot make it faster without heating the gas to higher temperatures, and you cannot heat the gas to higher temperatures without more energy input. Solar radiation at this distance provides a specific amount of energy, no more, no less, and that sets the upper limit on how fast the gas can move. Now let us talk about rockets. A chemical rocket works by combusting fuel and oxidizer in a chamber, producing high temperature, high pressure gases, and then expanding those gases through a nozzle. The nozzle converts the thermal energy and pressure into directed kinetic energy, accelerating the exhaust to very high velocities. A well-designed rocket nozzle can achieve exhaust velocities of 3 to 5 kilometers per second, and some advanced chemical propulsion systems push beyond that. Why is rocket exhaust so much faster than cometary outflow? Because the energy density is higher and because the expansion is controlled. In a rocket engine, you are not waiting for sunlight to slowly heat a surface. You are burning fuel that releases chemical energy at a rate determined by the combustion process, and you are channeling that energy through a nozzle that is specifically shaped to maximize the velocity of the exhaust. The result is gas moving 10 times faster than what natural sublimation can achieve. That factor of 10 is crucial. Remember the mass flux calculation from earlier. Mass flux is density times velocity times area. If you increase the velocity by a factor of 10, you can achieve the same momentum transfer with 1/10 the mass. Momentum is what matters when you're trying to push against the solar wind or when you are trying to change the trajectory of an object. A rocket producing exhaust at 3 to 5 kilometers per second needs far less propellant to generate the same thrust as a natural outflow at 0.4 kilometers per second. Let me put numbers to this. If 3i Atlas is using natural outgassing and needs to eject 5 billion tons per month to produce the observed jets, then switching to chemical rocket propulsion would reduce that requirement to roughly 500 million tons per month. That is still a huge amount of material, but it is just an order of magnitude less. More importantly, 500 million tons represents a much smaller fraction of the object's total estimated mass of 33 billion tons. Instead of losing 15% of its mass per month, it would be losing about 1.5%. That is still significant, but it is within the range of what a fuel tank could plausibly carry, and we are not done yet. Ion thrusters, which use electric fields to accelerate charged particles rather than relying on combustion, can reach exhaust velocities of 10 to 50 kilometers per second. At the upper end of that range, 50 kilometers per second, the required mass flux drops by another factor of 10 compared to chemical rockets. Now we are talking about 50 million tons per month, about 0.15% of the total mass. Suddenly the fuel requirement becomes almost negligible compared to the size of the object. This is not hypothetical technology. Ion thrusters exist, they fly on spacecraft right now. NASA's Dawn mission used ion propulsion to visit the asteroids Vesta and Ceres. The European Space Agency's Bepi-Colombo mission is using ion thrusters to reach Mercury. These are proven systems with well-understood performance characteristics. If a civilization more advanced than ours were building interstellar probes, it is entirely reasonable to assume they would use propulsion systems at least as efficient as ion drives, and possibly much more efficient. Let us imagine, just for the sake of argument, that 3i Atlas is using a propulsion system with exhaust velocities 100 times higher than natural cometary outflow. That would be 40 kilometers per second, well within the range of existing ion thruster technology. At that velocity, the required propellant to produce the observed jets drops to about 50 million tons per month, less than 0.2% of the object's mass. The object could sustain that level of thrust for months, without any noticeable change in its overall mass or size. Now let us think about what this means for the energy budget. Chemical rockets store energy in the chemical bonds of their fuel. When you burn hydrogen and oxygen to make water, you release about 15 million joules per kilogram of fuel. That is energy density that is simply not available from sunlight hitting a frozen surface. A rocket can release more energy per unit mass than solar heating can provide, and it can release that energy on demand whenever thrust is needed, rather than waiting for the sun to slowly warm the surface. Ion thrusters use electrical energy, which can be generated by solar panels or by onboard power sources like nuclear reactors. The Dawn spacecraft, for example, used solar panels to power its ion engines. At the distances 3i Atlas has been travelling, solar panels are still effective, and a sufficiently large array could generate the power needed to run ion thrusters continuously. The point is, if you allow for active propulsion, the energy problem disappears. You are no longer constrained by how much solar energy the surface can passively absorb. You are only constrained by how much energy you can store or generate on board. And for a designed system, that is an engineering problem with known solutions. Let us also talk about directionality. Natural cometary jets follow certain patterns. They are usually pointed away from the sun because solar radiation pressure and the solar wind push the gas in that direction. When you see jets that do not follow that pattern, when you see sunward jets or jets at odd angles, you need some additional mechanism to explain them. Rotation can cause jets to appear at different angles, and local topography like cliffs or craters can deflect out flowing gas. But those effects tend to be small, and they still result in jets that are primarily anti-sunward when averaged over time. Rocket thrusters, by contrast, can point in any direction you want. If you need thrust toward the sun, you point a thruster toward the sun. If you need thrust perpendicular to the sun, you orient your engines accordingly. The 7 distinct jets observed on November 8th could easily be explained as 7 separate thruster banks positioned around the object to provide multi-axis control. That is exactly how spacecraft attitude control systems work. Multiple small thrusters firing in coordinated patterns to control orientation and trajectory. The geometry of the jets on the 3i Atlas, the fact that they appear in multiple directions including sunward, is much easier to explain with active propulsion than with natural outgassing. It does not require special pleading about surface features or rotational states. It just requires that the object has thrusters, and that those thrusters are firing. There is another consideration, and it is one that often gets overlooked in these discussions: efficiency. Natural cometary outgassing is wildly inefficient as a propulsion mechanism. Most of the gas expands in all directions, not just in the direction that would be useful for changing the object's trajectory. The net thrust from cometary outgassing is the vector sum of all the individual gas molecules leaving the surface, and because they are leaving from multiple locations at multiple angles, much of that thrust cancels out. The non-gravitational acceleration we measure on comets is typically a small fraction of what you would get if all the outflowing mass were directed in a single optimal direction. Rockets by design are efficient. The nozzle ensures that almost all the exhaust is moving in the same direction, and that direction is chosen to maximize the change in velocity of the spacecraft. There is minimal waste, minimal cancellation, and maximum effectiveness per unit of propellant expended. If 3i Atlas is using rocket propulsion, it is using its fuel far more efficiently than natural outgassing ever could. Now, I want to address a question that might be on your mind. If 3i Atlas is using rockets, why does it look like a comet? Why is there a coma? Why are there jets? Why does it superficially resemble the natural objects we are familiar with? The answer is that rocket exhaust, especially from chemical rockets, produces gas and often entrained particles. That gas and those particles spread out around the spacecraft, forming a cloud that looks very similar to a cometary coma. The jets look like jets because they are jets, just powered by combustion rather than sublimation. In other words, an artificial object using chemical propulsion would not necessarily look obviously artificial. It would produce many of the same visual signatures as a natural comet, the coma, the jets, the tail structures. The difference would be in the details, in the velocities, in the mass loss rates, in the geometry, in all the things we have been discussing. The overall appearance might be similar enough to fool a casual observer, but detailed analysis would reveal inconsistencies with the natural model. And that is exactly what we are seeing. 3i Atlas looks enough like a comet that it was classified as one. But when you dig into the data, when you measure the jet velocities and the mass loss rates and the structural integrity, the natural explanation starts to break down. The deeper you look, the less it fits. Chemical rockets versus comet physics. One system requires enormous surface areas, implausible energy budgets, and structural resilience that natural objects do not possess. The other system uses proven technology, well-understood physics, and modest fuel requirements. One explanation forces you to make exception after exception to the standard model. The other explanation simply works. This does not prove that 3i Atlas is artificial. What it shows is that the artificial hypothesis is not ridiculous, not implausible, not easily dismissed. It is a viable alternative that fits the data at least as well as the natural hypothesis, and in many ways fits it better. Whether that alternative is correct will depend on additional observations, on spectroscopy that can measure the composition and velocity of the jets directly, on high-resolution imaging that can resolve surface features, and on continued monitoring as the object approaches Earth in December. But the comparison is instructive. It shows that we have the tools to distinguish between natural and artificial processes if we are willing to apply them rigorously. And it shows that 3i Atlas, whatever it is pushing us to think beyond the past, comfortable categories we are used to working with. Sometimes the universe hands you something that does not fit the existing boxes, and when that happens, the scientifically honest thing to do is build a new box. 1 in 100 million. The statistical nightmare. Statistics can be cold and impersonal, but they are also brutally honest. When you calculate the probability of a series of independent coincidences all occurring together, the numbers drop quickly, and when those probabilities reach certain thresholds, you have to start asking whether coincidence is really the right explanation. 3i Atlas presents us with a cascade of low probability events, and when you multiply those probabilities together, you end up with a number that is difficult to accept as random chance. Let us start with the trajectory. 3i Atlas is travelling on a retrograde orbit, meaning it is moving in the opposite direction to the planets around the Sun. That in itself is not unusual for an interstellar object. It could be approaching from any direction, and roughly half of all possible approach angles would result in retrograde motion. But here is what is unusual. The orbit of 3i Atlas is aligned to within 5 degrees of the ecliptic plane, the flat disk in which all the major planets orbit. Think about that for a moment. If you were throwing a dart at a sphere from a random direction in interstellar space, what are the odds that your trajectory would line up almost perfectly with the thin disk where all the planets happen to be? The ecliptic plane represents a tiny fraction of all possible approach angles. Most trajectories would come in steeply inclined, either from above or below the plane of the solar system, because most of the solid angle around the Sun is not in the ecliptic, but 3i Atlas came in almost level with the planets. Avi Loeb has calculated that probability. For a random interstellar trajectory to be aligned within 5 degrees of the ecliptic, the probability is about 0.2% or 1 in 500. That is already low, but it's not absurdly low. Rare things happen, and 1 in 500 is within the range of coincidence. But now let us add the next layer. 3i Atlas did not just pass through the inner solar system on an ecliptic-aligned trajectory, it passed close to multiple planets. On October the 3rd, it came within 29 million kilometers of Mars, which is roughly 0.19 astronomical units. That is close, very close in astronomical terms. Then it continued inward and approached Venus within 0.65 astronomical units. After perihelion, its trajectory will take it near Jupiter, coming within 0.36 astronomical units of the gas giant in March of 2026. Each of those close approaches is, by itself, somewhat unlikely. The solar system is mostly empty space, and hitting a narrow corridor that brings you within a few tens of millions of kilometers of a planet requires a fairly specific trajectory, but having your trajectory bring you close to Mars and Venus and Jupiter, all in sequence, is much less likely. The probability of that happening by chance depends on the exact definition of close and the range of trajectories you are considering, but Loeb has estimated it at about 0.005% when you account for the alignment with the ecliptic and the timing of the planetary positions. 0.005% is 1 in 20,000. We are starting to get into uncomfortable territory. Now let us talk about mass. The estimated mass of 3I Atlas, based on its size and assumed density, is at least 33 billion tons. That makes it roughly 1 million times more massive than 1I Oumuamua, the first confirmed interstellar object discovered in 2017. It is also about 1,000 times more massive than 2I Borisov, the second interstellar object discovered in 2019, and it is moving faster than both of them, with a hyperbolic excess velocity that places it among the most dynamically extreme objects ever recorded. Why does that matter? Because the distribution of interstellar objects by mass is expected to follow a power law, with small objects being far more common than large ones. This is the same pattern we see in asteroids and comets within our own solar system, and it is the pattern predicted by models of how planetary systems form and evolve. For every large object, there should be thousands or millions of smaller ones. The fact that we discovered a massive object like 3I Atlas so early in our survey, as only the third confirmed interstellar visitor, is statistically surprising. Loeb has calculated the odds of detecting an object of this size within the survey period we have been running, which is roughly a decade of systematic sky monitoring. If interstellar objects are distributed according to the standard mass function, the probability of finding something as massive as 3I Atlas before finding thousands of smaller objects is less than 0.1%. In other words, 1 in 1,000. But wait, there is more. The timing of 3I Atlas is also suspicious. It reached perihelion on October the 29th, 2025, at a point when it was hidden behind the Sun from Earth's perspective. That meant ground-based telescopes could not observe it during its most active phase, during the period when it was being heated most intensely, and when any breakup or major changes would have been most likely to occur. The object was essentially eclipsed by the Sun at the exact moment when the most interesting things were happening. That eclipse was not total, and it was not permanent. Spacecraft like SOHO and Stereo, which observed the Sun from different vantage points, were able to track 3I Atlas during perihelion, and Mars orbiters, as we have discussed, were able to capture images from their unique perspective. But from Earth, our largest telescopes, our best ground-based instruments, were blind to the object for several weeks. Is that timing suspicious? It depends on how you frame the question. If you are designing a mission, and you want to perform a maneuver near the Sun without being observed from Earth, perihelion is an excellent time to do it. The Sun acts as a natural shield, blocking the line of sight and making it impossible for Earth-based observers to see what you're doing. In spacecraft mission design, this is sometimes called a solar oberth maneuver, when used for gravitational assists, and it can be an effective way to change velocity while minimizing observability. For a natural comet, the timing is just random. Perihelion happens when it happens based on the orbital parameters, and whether that coincides with a solar eclipse from Earth's perspective is pure chance. But the fact that it did coincide, combined with all the other low probability factors we have been discussing, adds another small weight to the scale. Loeb has also pointed out the arrival time. 3I Atlas was discovered in July of 2025 and reached perihelion in late October. That gave the scientific community just a few months to organise observations, obtain telescope time, and coordinate follow-up studies. If the goal were to minimise scrutiny while maximising close approaches to planets, this timing would be nearly optimal. Long enough to be detected so we know something is here, but short enough that detailed campaigns are difficult to mount. Again, for a natural object, this is just how the dice rolled, but when you start stacking up all these low probability events, coincidence becomes harder and harder to swallow. Let me be very explicit about the multiplication of probabilities. If you have multiple independent events, each with their own probability, the probability of all of them happening together is the product of the individual probabilities. So if event A has a 0.2% chance and event B has a 0.5% chance, and event C has a 0.1% chance, the probability of A and B and C all happening together is 0.2 times 0.5 times 0.1%, which equals 0.01% or 1 in 10,000. For 3i Atlas, we have the trajectory alignment, 0.2%. We have the close planetary approaches, contributing another factor that brings us down to 0.005%. We have the mass anomaly, less than 0.1%. When you multiply these together, you get probabilities in the range of 1 in several million. And we have not even included all the other anomalies, the sunward jets, the survival through perihelion, the unusual nickel-to-iron ratio in the coma, the lack of a conventional tail. Each of those adds another factor, another layer of improbability. By the time you go account for everything, you are looking at odds of 1 in 100 million or worse. 1 in 100 million is the kind of number that makes statisticians very uncomfortable. It is not impossible, but it is so unlikely that you have to seriously consider whether your assumptions are wrong. Maybe these events are not independent. Maybe there is some underlying physical mechanism that makes them all more likely to occur together. Or maybe, just maybe, the object is not random. If 3i Atlas were designed, if it was sent here intentionally by some intelligence, then none of these probabilities are surprising. An engineered trajectory would naturally aim for the ecliptic because that is where the planets are. Close approaches to multiple planets would be a feature, not a bug, part of the mission designed to gather data or perform flybys. The timing of perihelion during solar eclipse from Earth could be deliberate, a way to perform orbital adjustments with minimal observation. The mass and velocity would be chosen based on mission requirements, not constrained by the natural distribution of interstellar debris. In the design scenario, all the low probability coincidences become high probability mission features. The statistics flip from working against the hypothesis to working for it. This is not proof. Statistics never prove anything, they only tell you what is likely and what is unlikely. But they are a tool. And when that tool is pointing you toward an uncomfortable conclusion, it is worth paying attention. 1 in 100 million does not mean impossible, but it does mean that you should be looking very carefully at your assumptions and at alternative explanations. The natural explanation requires us to accept that we got extraordinarily lucky, that the third interstellar object we detected just happened to be enormous, just happened to align with the ecliptic, just happened to pass close to multiple planets, just happened to reach perihelion when Earth could not see it, and just happened to display a whole host of other anomalies that we are still trying to explain. That is a lot of luck. The artificial explanation requires us to accept that intelligent life exists elsewhere in the galaxy, that it builds interstellar probes, and that one of those probes is currently passing through our solar system. That is a big assumption, arguably a much bigger assumption than extraordinary luck. But it is an assumption that does not require us to dismiss the data or explain away the statistics. It takes the observations at face value and offers a hypothesis that fits. Which assumption is more reasonable? That depends on your priors, on what you think is more likely to be true before you even look at the data. If you start with the belief that intelligent life is extremely rare or non-existent, then no amount of statistical improbability will convince you to consider the artificial hypothesis. You will always find a way to explain the observations as natural, no matter how convoluted that explanation becomes. But if you start with the belief that intelligent life is plausible, that it might arise on planets around other stars, and that some fraction of those civilizations might build technology capable of interstellar travel, then the statistics become compelling. 1 in 100 million is not a probability you can easily ignore. Science is supposed to follow the evidence. When the evidence points towards something unusual, something outside the standard model, the correct response is not to reject it out of hand, but to investigate more carefully, to design tests that can distinguish between the competing hypotheses, and to let the data decide. That is what is happening now with 3i Atlas. Observations are being planned, measurements are being taken, and the scientific community is slowly, carefully working through the implications. The statistical nightmare of 3i Atlas is that it does not want to fit into the natural box. Every time you try to calculate the odds of all these features occurring together by chance, the numbers scream at you that something is off. Whether that something is our incomplete understanding of interstellar object populations, or whether it is the presence of technology in our solar system, is the question we are now trying to answer. And that question, more than anything else, is what makes this moment in astronomy so extraordinary. We are not just studying a comet or even just an interstellar visitor. We are confronting probabilities that force us to consider possibilities we have never seriously had to consider before. The universe is putting a question in front of us, and we do not yet know the answer. But we are looking, we are calculating, and we are following the numbers wherever they lead. 7 jets and the thruster hypothesis. On the morning of November 8th, 2025, at 4:10 Universal Time, 3 astronomers pointed their instruments at 3I Atlas and captured something that has not stopped generating discussion since. Michael Jaeger, Gerald Raymond, and Enrico Prosperi, working from their observatory, stacked 24 exposures in the green filter along with additional exposures in red and blue, and what emerged from that data was a structure so organised, so geometrically precise, that it challenges the assumption of natural chaos we usually associate with comets. At least 7 distinct jets, each emanating from the nucleus, each pointing in a different direction, creating a pattern that looked less like the random venting of a comet and more like the deliberate configuration of a propulsion system. 7 separate streams of material, visible simultaneously, arranged around the central body in a way that suggests coordination rather than accident. Let me describe what we are seeing in that image. The nucleus sits at the centre, a bright point that represents the solid body of 3I Atlas. Radiating outward from that central point are the jets, elongated structures of gas and dust that extend hundreds of thousands of kilometres into space. Some of them point roughly toward the Sun, those are the anti-tail features we have been discussing. Others point away from the Sun, which is the expected direction for normal cometary jets. Still others point at intermediate angles, neither directly sunward nor directly anti-sunward, but somewhere in between. The fact that we can see 7 distinct jets means they are not merging into a single diffuse cloud. Each jet maintains its identity, its collimation, its separation from the others. That is structure. That is organisation, and it is very difficult to produce through random outgassing. Natural comets do have multiple jets. We have observed this on other objects. The jets form at active areas on the surface where subsurface ice is exposed to sunlight, and the location of those active areas is determined by the geology and the rotation state of the comet. As the nucleus spins, different areas rotate into sunlight and become active, creating jets that appear at different angles depending on the viewing geometry and the time of observation. But there is a difference between having multiple jets that appear at different times due to rotation and having 7 jets that are all visible at the same time pointing in distinctly different directions. For 7 jets to be simultaneously visible and spatially separated, they need to be coming from different locations on the nucleus that are all in view at once. That requires either a very specific viewing angle, or a nucleus that has active areas distributed all over its surface. For a natural comet, having that many simultaneously active regions is unusual. Most comets have 1 or 2 dominant jet sources at any given time, with perhaps a few weaker secondary sources. The number of active regions is limited by how much of the surface is actually covered with volatile ices versus inert dust and rock. If 3I Atlas has 7 distinct sources all active at once, that suggests a very high fraction of the surface is composed of or covered with material that can sublimate. And yet Hubble observations suggested the surface is relatively dark, not the bright icy surface you would expect from a highly volatile, rich object. There is also the question of symmetry. The 7 jets are not randomly scattered, they form a pattern. Some are paired, pointing in roughly opposite directions, which is what you would expect if the object were venting from 2 sides. Others fill in the gaps, creating what almost looks like a hub and spoke arrangement. That kind of symmetry does not usually arise from random geological processes. Let me contrast this with what we see on human spacecraft. When engineers design a spacecraft that needs attitude control, the ability to rotate and orient itself in space, they use multiple thrusters arranged strategically around the body. A typical design might have clusters of small thrusters at different locations, each cluster capable of firing in different directions, so that any desired rotation or translation can be achieved by firing the appropriate combination of thrusters. The number of thrusters depends on the mission requirements, but having 6 to 8 thruster positions is common for a spacecraft that needs full 3-dimensional control. Each thruster provides force in a specific direction, and by coordinating which thrusters fire and for how long, the flight computer can execute complex maneuvers. This is not exotic technology, this is standard practice for satellites, space probes, and crewed spacecraft. Now, if you were observing a spacecraft from a distance and you could not resolve the individual thrusters, but you could see the exhaust plumes, what would you see? You would see multiple jets of gas emanating from different points on the body, each jet pointing in the direction that thruster is firing. And if the spacecraft were actively maneuvering, you might see several of those jets active at the same time, creating a multi-jet structure that looks organized because it is organized. The 7-jet structure on 3i Atlas fits that pattern almost exactly. It looks like a multi-thruster configuration. It looks like something designed to provide propulsion and control in multiple directions. And while that does not prove it is artificial, it is certainly consistent with the hypothesis. There is another detail worth noting. The report from the November 8th observations mentions that the jets are not all equally bright. Some are stronger, more prominent, while others are weaker, fainter. That variation in intensity suggests that different sources are producing different amounts of material, or that they are being observed at different angles relative to our line of sight. For a natural comet, that variation could be explained by differences in the amount of ice at each active area, or differences in how directly sunlight is hitting each location. For a thruster system, it could be explained by different thrusters firing at different power levels depending on what maneuver is being executed. The non-gravitational acceleration detected in 3i Atlas supports the thruster interpretation. Non-gravitational acceleration means the object is not moving purely under the influence of gravity, it is being pushed by something else. For a comet, that push comes from the recoil of outgassing, the rocket effect of gas escaping from the surface. For a spacecraft, it comes from thrusters. The key difference is the efficiency and directionality. Natural outgassing produces thrust in all directions, and most of that thrust cancels out. The net acceleration is usually small and difficult to measure. Thrusters, by contrast, produce thrust in specific directions, and the net acceleration is much larger for a given amount of expelled mass. The fact that 3i Atlas is showing measurable non-gravitational acceleration, and that this acceleration is occurring in the presence of these highly structured jets, suggests that the jets are producing directed thrust, not just random venting. Let me address a potential objection. If 3i Atlas has thrusters, and if those thrusters are firing to produce the observed jets, why has the trajectory not changed more dramatically? Why is the non-gravitational acceleration relatively modest rather than causing large deviations from the predicted orbit? The answer is that we do not know what the mission profile is. If this is a reconnaissance probe, a passive observer designed to fly through the inner solar system and gather data, then large trajectory changes might not be necessary or desirable. Small adjustments to fine-tune the orbit, to aim for specific planetary flybys, or to correct for perturbations would be sufficient. You would not need to fire the thrusters at full power, you would just need enough thrust to maintain control. Alternatively, if the thrusters are being used primarily for attitude control, for keeping the spacecraft oriented in a specific direction, then the net acceleration could be small even though individual thrusters are firing frequently. Attitude control maneuvers involve firing thrusters in opposing pairs to create torque without creating net translation. The object spins or tilts, but it does not accelerate significantly in any particular direction. The November 8th image shows jets pointing in opposite directions, which is exactly what you would see during an attitude control burn. Fire one thruster to rotate clockwise. Fire the opposite thruster to stop the rotation. The result is a change in orientation with minimal change in velocity. Another consideration is fuel management. If this is an interstellar probe that has been travelling for potentially millions or billions of years, conserving propellant would be a priority. You would not waste fuel on unnecessary manoeuvres. You would plan your trajectory carefully, using gravity assist from planets where possible, and only firing thrusters when absolutely needed. The modest non-gravitational acceleration we are observing could be the signature of a very fuel-efficient mission design. The timing is also interesting. The non-gravitational acceleration was first clearly detected in data from late October, around the time of perihelion. Prior to that, from July through September, there was no detectable acceleration. The object was coasting, moving purely under gravity. Then, as it approached perihelion, the acceleration kicked in. That timing suggests the thrusters were turned on for a specific purpose, perhaps to perform a manoeuvre during the perihelion passage when the Sun's gravity could be used to amplify the effect of thrust through an Oberth manoeuvre. An Oberth manoeuvre is a technique where you apply thrust at the point of closest approach to a massive body, in this case the Sun, to maximise the change in orbital energy. The same amount of thrust applied at perihelion has a much larger effect on the final trajectory than thrust applied when you are farther away. If 3I Atlas were trying to alter its path through the solar system, perihelion would be the optimal time to do it. And that is exactly when the jets became most active and the non-gravitational acceleration became measurable. The 7-jet structure is not the only time we have seen complex geometry from 3I Atlas. Other observations have shown varying numbers of jets at different times, sometimes fewer, sometimes more, depending on the observing conditions and the state of the object. That variability is consistent with a system where different thrusters are activated at different times for different purposes. It is less consistent with a static geological structure where active areas are fixed in place. One more point about the geometry. The jets on 3I Atlas are collimated, meaning they maintain a relatively narrow beam rather than spreading out into a wide cone. Collimated jets are characteristic of nozzles, where the flow is directed and shaped by the geometry of the exhaust channel. Natural sublimation tends to produce more diffuse outflows because the gas is expanding freely from an open surface without any structure to constrain it. The fact that the jets maintain their collimation over distances of hundreds of thousands of kilometres suggests they were emitted with some degree of directionality, which is easier to achieve with a nozzle than with bare ice. Is this proof? No. Could all of this be explained by an unusual but ultimately natural comet with multiple active areas and favourable viewing geometry? Possibly. But the accumulation of details, the 7 jets, the symmetry, the variability, the collimation, the timing of the non-gravitational acceleration, all of it fits more naturally into the thruster hypothesis than into the natural outgassing hypothesis. The beauty of the thruster hypothesis is that it is testable. If 3I Atlas is using rocket propulsion, then the exhaust should have specific characteristics. The velocity of the gas should be higher than natural sublimation can produce. The composition might show combustion products or ionized particles depending on what type of propulsion system is being used. The jets should respond to changes in the object's needs for thrust and control, becoming more or less active in coordinated ways rather than following the passive heating cycle of a comet. All of those are things we can measure with the right instruments. Spectroscopy can tell us the velocity and composition. High-resolution imaging can resolve the individual jet sources and see if they correspond to discrete points on the surface like thruster nozzles would. Continuous monitoring can track whether the jets turn on and off in patterns consistent with active control systems. The observations are being planned, the instruments are being prepared, and in the coming weeks we will have data that can either support or refute the thruster hypothesis. That is how science works. You form a hypothesis, you make predictions, and you test them. The 7 jets of 3I Atlas have given us a hypothesis that is specific enough to test and bold enough to matter. Now we get to see if it holds up. The Borisov connection that wasn't unknown, November the 2nd, 2025, while 3I Atlas was still hidden behind the Sun from Earth's perspective, astronomer Genndy Borisov made another discovery. Borisov, whose name is already attached to 2I Borisov, the second confirmed interstellar object found in 2019, identified a new object moving through the inner solar system. It was designated C2025V1, and almost immediately speculation began that it might be connected to 3I Atlas. The timing seemed too coincidental. Here was 3I Atlas, an interstellar visitor creating headlines and raising questions about its nature, and suddenly another object appears, discovered during the brief window when 3I Atlas was unobservable from Earth. Some observers on social media began asking whether C2025V1 could be a secondary object, perhaps a probe or a fragment deployed by 3I Atlas during its perihelion passage. The conspiracy angle was obvious. One interstellar mothership arriving and releasing a smaller craft to explore the solar system more closely. Avi Loeb addressed this speculation directly in a blog post, and his analysis was clear. C2025V1 is not related to 3I Atlas. The orbits do not match. The trajectories do not intersect at any reasonable point, and without invoking active propulsion beyond what has been measured, there is no way for the two objects to have been close enough to each other for one to have deployed the other. Let me walk through the details. C 2025 V1 has an orbital eccentricity of 1.0095 with an uncertainty of 0.0026. An eccentricity greater than 1 means the orbit is unbound, hyperbolic, which would technically make it an interstellar object. But the uncertainty is large enough that the true eccentricity could be slightly less than 1, which would mean the object is actually bound to the Sun, originating from the Oort cloud at the outer edges of the solar system rather than from interstellar space. The orbital inclination of C 2025 V1 is 113 degrees relative to the ecliptic plane. That is a steeply inclined orbit, nearly perpendicular to the plane of the planets. For reference, 3I Atlas has an inclination of about 175 degrees, which is also steep but in the opposite sense. It is retrograde and nearly aligned with the ecliptic. The two orbital planes are not even close to being coplanar. They are tilted at very different angles, which means the objects are not travelling in the same general direction. When you work out the geometry, the closest the two orbits come to each other in space is about 75 million kilometres, or 0.5 astronomical units. That is half the distance from the Earth to the Sun, which sounds close on a cosmic scale, but is actually enormous when you're talking about objects trying to rendezvous. And even that closest approach between the orbits does not mean the objects themselves were ever that close. The objects have to actually be at those positions at the same time for a rendezvous to occur. Loeb calculated that without active propulsion, the two objects were never closer than 225 million kilometres, or 1.5 astronomical units from each other. That is farther than the distance from the Earth to Mars at their closest approach. You cannot deploy a probe across that kind of distance using any passive mechanism. You would need active propulsion, and a lot of it, to bridge that gap. The measured non-gravitational acceleration of 3I Atlas is insufficient to close that distance in the time available. We have data on how much thrust 3I Atlas is producing, and while it is measurable, it is not enough to explain a separation maneuver that would place C 2025 V1 on its current trajectory. The delta V, the change in velocity required, is simply too large, so the connection does not work. C 2025 V1 is not a probe from 3I Atlas, at least not based on the trajectories we can measure. But the speculation was not entirely without merit, and it highlights an interesting pattern in how people are thinking about 3I Atlas. The idea that 3I Atlas might be a mothership, that it might carry smaller probes or instruments that could be deployed during its passage through the solar system, is not new. Loeb himself has suggested this possibility in earlier writings. If you were designing an interstellar mission to survey a star system, sending a single large craft with multiple deployable modules would be an efficient approach. The mothership provides propulsion, power, and communications, while the smaller probes spread out to visit different targets or gather data from multiple locations simultaneously. It is a sensible mission architecture, and it is exactly the kind of thing human mission planners consider when designing robotic exploration missions. The fact that C 2025 V1 appeared during the 3I Atlas flyby, and the fact that it also has an unusual orbit, made the connection plausible enough to investigate. The investigation showed the connection does not hold, but the instinct to look for it was scientifically sound. Now, let me tell you what C 2025 V1 actually is, or at least what it most likely is. Based on its orbital parameters and the uncertainty in those parameters, it almost certainly originated from the Oort cloud. When you integrate its orbit backward in time, taking into account gravitational perturbations from the planets, the eccentricity drops below 1, indicating a bound orbit. A small gravitational kick from Jupiter during its perihelion passage could have increased the eccentricity enough to make it appear slightly hyperbolic when measured now, but that does not mean it is truly interstellar. The Oort cloud is a vast spherical shell of icy bodies that surrounds the solar system at distances of tens of thousands of astronomical units. Objects in the Oort cloud are only loosely bound to the Sun, and occasionally one gets perturbed by a passing star or a galactic tide and falls inward toward the inner solar system. When that happens, the object can arrive on a nearly parabolic orbit, meaning its eccentricity is very close to 1. Depending on how it interacts with the planets, that eccentricity can increase slightly, making it look like the object might be unbound. C 2025. V1 fits that profile perfectly. It has a steep inclination, which is characteristic of Oort cloud objects because the Oort cloud is spherical and objects can fall in from any direction. It has an eccentricity close to 1, which is what you expect for something on its first passage through the inner solar system. And it does not show clear signs of being interstellar when you account for the measurement uncertainties. So why did Borisov discover this object now? Pure coincidence. Borisov is an active observer who spends a lot of time searching for comets and near-Earth objects. He uses capable equipment and he knows where to look. The fact that he found C 2025 V1 during the same time frame as 3I Atlas is interesting, but it is not evidence of a connection. It is just what happens when a skilled astronomer is paying attention to the sky during a period of heightened interest in unusual objects. There is one other detail worth mentioning. Like 3I Atlas, C 2025 V1 does not display a clear cometary tail in the available images. That similarity led some to speculate that the two objects might be related or might share some common property. But the absence of a visible tail can have many explanations. The object might be observed at an angle where the tail is not prominent, or it might be far enough from the sun that sublimation is minimal, or it might be composed of material that does not produce much dust. The lack of a tail is not a unique signature that links the two objects. The key lesson from the C 2025 V1 episode is the importance of doing the math. Speculation is fine, it drives curiosity and it motivates investigation. But speculation has to be checked against the data. When you work through the orbital mechanics, when you calculate the required delta V and compare it to the measured accelerations, the connection between 3I Atlas and C 2025 V1 falls apart. The numbers do not support it, and that is the end of the story. But the episode also reveals something about the current state of 3I Atlas research. People are primed to look for connections, to see patterns, to find evidence of something more than a simple comet. That heightened state of attention is both a strength and a weakness. It is a strength because it means people are paying close attention, scrutinizing the data, and not taking anything for granted. It is a weakness because it can lead to seeing patterns that are not really there, connecting dots that should not be connected, and mistaking coincidence for causation. Science requires skepticism in both directions. Skepticism toward the conventional explanation, because sometimes the conventional explanation is wrong, but also skepticism toward the extraordinary explanation, because extraordinary claims require extraordinary evidence. The C20-25 V1 connection was worth investigating precisely because it was testable. The orbits are known, the distances can be calculated, and the hypothesis can be evaluated. When it does not hold up, you move on. 3I Atlas does not need C20-25 V1 to be interesting. The anomalies we have been discussing, the sunward jets, the mass loss, the survival through perihelion, the statistical improbabilities, those are all real and those are all sufficient to make this object one of the most compelling mysteries in astronomy right now. Adding a speculative connection to another object does not strengthen the case. It distracts from the actual evidence. And that is an important principle. When you have a strong case based on multiple independent lines of evidence, you do not need to reach for additional speculative connections. The data should speak for itself. If 3I Atlas is artificial, we will know because the measurements will confirm it, not because we found some other object that might or might not be related. The Borisov connection was an interesting idea, and it received the attention it deserved. It was investigated, analysed, and ultimately rejected based on the evidence. That is exactly how the process should work. Speculate, test, evaluate, and let the data decide. The fact that this particular speculation did not pan out does not diminish the larger questions surrounding 3I Atlas. It just reminds us that not every unusual thing that happens in the sky is connected to every other unusual thing, and that sometimes a coincidence is just a coincidence. C20-25 V1 will continue on its trajectory, whether it is a true interstellar visitor or an Oort cloud object. 3I Atlas will continue on its trajectory, with or without any connection to other objects. And we will continue to observe, measure, and analyze, following the evidence wherever it leads, testing every hypothesis that can be tested, and being honest about what the data does, and does not support. That is science. Not the confirmation of what we want to believe, but the careful, methodical evaluation of what the universe is actually showing us. December 19th, when Earth gets its closest look. Mark your calendar, December 19th, 2025. On that date, 3I Atlas will make its closest approach to Earth, passing within 269 million kilometers of our planet. That is roughly 1.8 astronomical units, still far beyond the orbit of Mars, but close enough that it represents the best opportunity we will ever have to study this object with the Earth-based instruments. Close enough that the Hubble Space Telescope and the James Webb Space Telescope can obtain data with unprecedented detail. Close enough that we might finally get the answers to questions that have been building since July. Let me put that distance in perspective. 269 million kilometers is about 1.8 times the distance from Earth to the Sun. It is not close in its everyday terms. You're not going to see 3I Atlas with the naked eye, and it is not going to fill telescope eyepieces with spectacular views. But in astronomical terms, for an object that is travelling through interstellar space, this is as good as it gets. After December 19th, 3I Atlas will continue to recede, growing fainter and smaller, until it eventually disappears from view as it leaves the solar system and returns to the vast emptiness between the stars. This is a one-time opportunity. 3I Atlas is not going to swing back around for another pass. It is not on an elliptical orbit that will bring it back in a few decades or centuries. It is on a hyperbolic trajectory, unbound from the Sun, and once it leaves, it is gone. Every observation we make between now and December 19th is precious because we will not get another chance. So what are we going to do with that opportunity? What observations are being planned and what questions are we trying to answer? First, high-resolution imaging. Both Hubble and Webb will be pointed at 3I Atlas during the approach. Hubble has already imaged the object once, back in July, and that image showed the nucleus surrounded by a coma with hints of structure. But July was early in the encounter, when 3I Atlas was still relatively far from the Sun and not yet at peak activity. December is post-perihelion, after the object has been through its closest approach to the Sun, after it has experienced maximum heating and maximum mass loss. Comparing the December images to the July images will tell us whether the object has changed. Are there new features? Has the size of the coma increased or decreased? Are there signs of fragmentation that were not present before? Is the nucleus still a single bright point, or has it resolved into multiple components? These are straightforward observational questions, and high-resolution imaging can answer them. Webb, with its infrared capabilities, can probe deeper into the coma and potentially see through the dust to get a better look at the nucleus itself. Infrared wavelengths are less affected by scattering from small particles, which means Webb can see structures that might be hidden at visible wavelengths. If there are discrete sources of emission on the nucleus, if the jets are coming from specific points rather than from a diffuse surface, Webb should be able to resolve that. Second, spectroscopy. This is the big one, the measurement that has the potential to definitively distinguish between natural outgassing and active propulsion. Spectroscopy breaks down the light from an object into its component wavelengths, revealing the chemical composition and physical state of the material. For 3I Atlas, spectroscopy can tell us what the jets are made of, how fast they are moving and what temperature they are at. If the jets are driven by natural sublimation, the gas should be moving at velocities consistent with thermal expansion, around 0.4 kilometers per second. The composition should be dominated by common cometary volatiles like water, carbon dioxide, carbon monoxide, and simple hydrocarbons. The emission lines should be relatively narrow, indicating gas at a few hundred degrees Kelvin. If the jets are driven by chemical rockets, the velocities should be higher, 3 to 5 kilometers per second or more. The composition might show combustion products, things like water vapor from hydrogen, oxygen combustion or nitrogen compounds if hydrazine-based fuels are being used. The emission lines might be broader, indicating higher temperatures and more turbulent flow. If the jets are driven by ion propulsion, the story changes again. Ion thrusters produce highly ionized gas moving at extremely high velocities, 10 to 50 kilometers per second. The spectroscopy would show strong ionization lines, narrow velocity distributions because ion beams are collimated, and potentially on unusual compositions depending on what propellant is being used. Each of these scenarios produces a different spectroscopic signature, and those signatures are measurable. This is not guesswork or interpretation. This is physics. The data will tell us what is happening. Third, photometry and light curves. By monitoring the brightness of 3I Atlas over time, we can learn about its rotation state and its surface properties. If the object is rotating, the brightness should vary periodically as different parts of the surface rotate into view. The amplitude of that variation tells us how much the reflectivity varies across the surface, which in turn tells us something about the composition and structure. If 3I Atlas is a natural comet with an irregular shape and a patchy surface, we would expect to see brightness variations on the order of tens of % over a rotation period of hours to days. If it is a more symmetric object, artificial or yes, otherwise the variations might be smaller or follow a different pattern. Long-term monitoring can also reveal whether the object is in a stable rotation state or whether it is tumbling, which would indicate that torques from outgassing or other forces are affecting its spin. Fourth, astrometry. Precise measurements of the object's position over time can reveal whether the non-gravitational acceleration is continuing, changing, or has stopped. If 3I Atlas performed a maneuver at perihelion and is now coasting, the acceleration should have decreased to near zero by December. If it is still actively adjusting its trajectory, the acceleration should persist. By tracking the position with high precision and comparing it to the predicted trajectory based on gravity alone, we can see if there are ongoing deviations. Astrometry can also detect changes in the direction of the non-gravitational force. If the jets are being reoriented, if the thrust vector is changing over time, that will show up as changes in the direction of the deviation from the gravitational orbit. This is another way to test whether the object is under active control or just venting gas in a passive manner determined by solar heating and rotation. Fifth, radar. This is a long shot because 3I Atlas will be far away and radar returns from such distances are weak. But some of the most powerful planetary radar systems, like the Goldstone Solar System radar in California and the Arecibo replacement facilities, if they become available, might attempt to bounce signals off the object. Radar can measure the size, shape, and surface properties in ways that optical imaging cannot. It can penetrate the coma and get a direct look at the nucleus, and it can measure the rotation rate with high precision. If radar observations are successful, they could provide the clearest evidence yet of whether 3I Atlas is a rubble pile, a solid object, or something with internal structure. Radar can distinguish between a porous, spongy texture and a smooth, dense surface. It can see asymmetries and irregularities that are too small to resolve with optical telescopes. And it can do all of this without depending on sunlight or surface brightness. All of these observations are being planned by multiple teams around the world. Professional observatories are competing for telescope time, submitting proposals and coordinating schedules to maximize coverage. Amateur astronomers with capable equipment are also participating, contributing data that complements the professional observations and fills in gaps in the timeline. The scientific community is mobilizing for December 19th in a way that rarely happens outside of major astronomical events like eclipses or planetary conjunctions. This is not just another comet. This is an interstellar visitor displaying anomalies that demand explanation. And the opportunity to study it up close is driving an unprecedented level of effort. But there is also a sense of urgency because data time is limited. 3I Atlas is moving at over 130,000 kilometers per hour relative to the Sun. Every day it gets farther away, every week it gets fainter, and every month it becomes harder to observe. By early 2026, it will be beyond the range of most ground-based telescopes. By mid-2026, only the largest instruments will be able to track it. By late 2026, it will be gone, a fading speck disappearing into the interstellar night. December 19th is not just the closest approach, it is the beginning of the end of our opportunity to study this object. After that date, we will be working with the data we collected, analysing it, debating it, writing papers about it. But the active phase of an observation, the time when we can still point telescopes at 3I Atlas and gather new data, will be winding down. That creates pressure. Pressure to get the observations right, to use the limited telescope time wisely, to prioritise the measurements that will provide the most definitive answers. There is no second chance here. No opportunity to go back and redo an observation if it does not turn out well. This is it. The results will not come immediately. Spectroscopy takes time to process. Light curves require days or weeks of monitoring to reveal patterns, and astrometry needs multiple measurements spread over time to detect small deviations. We will not wake up on December 20th with all the answers, but we will start to see data coming in, preliminary results being shared at conferences and on preprint servers, and the picture will gradually become clearer. If the spectroscopy shows velocities consistent with natural outgassing, if the composition is typical of comets, if the imaging shows a fragmented nucleus surrounded by a dispersing debris cloud, then the natural explanation will be strengthened. We will have learned that 3I Atlas is an unusual comet, perhaps an extreme example of cometary behaviour, but ultimately explicable within the framework of known physics. If the spectroscopy shows higher velocities, unusual compositions or ionization signatures, if the imaging shows a single intact body with discrete emission sources, if the astrometry shows continuing non-gravitational acceleration with changing thrust vectors, then the artificial hypothesis will become much harder to dismiss. We will be forced to seriously consider that we are looking at technology, that we are observing the exhaust from propulsion systems, and that 3I Atlas is not a natural object. December 19th is when the universe gives us the data we need to make that determination. It is when speculation ends and measurement begins. It is when we find out whether the anomalies we have been discussing are real or artifacts of incomplete observations. It is the moment when 3I Atlas either fits into the existing boxes or forces us to build new ones. And regardless of which way it goes, regardless of what the data shows, it will be one of the most important sets of observations in the history of astronomy. Because we will have studied an interstellar visitor at close range, we will have applied the full toolkit of modern astrophysics to an object from beyond our solar system, and we will have pushed the boundaries of what we can learn from distant observations. December 19th. The date is set, the telescopes are ready, and the world is watching. This is when we find out what 3I Atlas really is. The bet, the breakthrough, and what happens next. On November the 10th, 2025, Avi Loeb made a bet. Not a casual wager with a colleague over coffee, but an official bet registered with the Long Now Foundation, an organisation that specialises in long-term thinking and long-duration bets about the future. The bet was with Michael Shermer, Executive Director of the Skeptic Society, and the stakes were not trivial. Loeb wagered that within 5 years, by December 31st, 2030, there will be undisputable scientific evidence for a technological artifact from an extraterrestrial civilization. The timing of this bet is not coincidental. Loeb has been arguing for months that 3I Atlas displays characteristics inconsistent with a natural comet, and that the artificial hypothesis deserves serious consideration. By formalizing a bet, he is putting his reputation and his credibility on the line in a very public way. If he is right, if evidence emerges within 5 years that confirms the existence of extraterrestrial technology, his position will be vindicated. If he is wrong, if no such evidence appears, he will have been proven overly optimistic or premature in his conclusions. But the bet is not really about money or about being right. It is about shifting the conversation. For decades, the search for extraterrestrial intelligence has been largely confined to radio SETI, scanning the skies for artificial signals in the electromagnetic spectrum. That approach has value, but it is based on the assumption that advanced civilizations would choose to broadcast their presence using radio transmissions. If they do not, if they remain silent, or if they communicate in ways we have not thought to look for, then Radio SETI will never find them. Loeb's approach is different. He's advocating for artifact SETI, the search for physical objects rather than signals. If civilizations build interstellar probes, if they send spacecraft to explore other star systems, if they leave behind evidence of their technology in the form of megastructures or engineered objects, then we might find that evidence by looking at things that pass through our solar system or orbit nearby stars. 3I Atlas in this framework is not an outlier. It is a prototype. It is the first object we have examined closely enough to raise serious questions about its origin, and whether it turns out to be natural or artificial. The exercise of examining it is pushing the field forward. The bet also serves another purpose. It draws attention. Bets, especially bets between prominent figures, get media coverage. They get people talking, they spark debates, and they bring public attention to questions that might otherwise remain confined to academic journals. By betting that we will find evidence of extraterrestrial technology within 5 years, Loeb is making a bold claim that forces people to engage with the question. You cannot dismiss the idea as fringe or unserious when someone with Loeb's credentials is willing to stake his reputation on it, and the timing matters. The next 5 years will see the launch and operation of several new observatories and missions that are specifically designed to find and characterize small objects in the solar system. The Vera Rubin Observatory, which discovered 3I Atlas, will continue surveying the sky and detecting interstellar visitors. The Galileo project, which Loeb founded and directs, is building dedicated observatories to search for anomalous aerial phenomena and potential extraterrestrial artifacts. These tools and projects increase the probability of finding something, and Loeb is betting that they will succeed. But beyond the bet, beyond the public attention and the scientific debate, there is a deeper question at play. What happens if we actually do find evidence of extraterrestrial technology? What are the consequences for humanity, for science, for our understanding of our place in the universe? First, the scientific implications. Confirming the existence of extraterrestrial technology would be the most important discovery in the history of science. It would answer one of the oldest and most profound questions humans have ever asked. Are we alone? And the answer would be no. That single piece of knowledge would reshape entire fields of study. Astrobiology would shift from speculative to observational. SETI would be validated as a legitimate scientific endeavour. Planetary science would have to incorporate the possibility that some objects we observe are not natural. It would also force us to reckon with our assumptions about intelligence, technology, and the probability of life. If we find even one example of extraterrestrial technology, it suggests that technological civilizations are not impossibly rare. It suggests that the universe is, or has been, populated with beings capable of building machines and exploring space. That has implications for the Drake equation, for the Fermi paradox, and for every model we have built to estimate the prevalence of intelligent life. Second, the philosophical implications. For thousands of years, humans have wondered whether we are unique, whether life and intelligence are exclusive to Earth, whether the universe is fundamentally hospitable or hostile to beings like us. Finding extraterrestrial technology would provide an answer, and that answer would fundamentally alter how we see ourselves. We would no longer be the only technological species in the cosmos. We would be part of a broader community, or at least we would know that such a community exists or existed. That shift in perspective could be destabilizing, or it could be inspiring. It could lead to existential anxiety, the fear that if other civilizations are out there, they might be more advanced, more powerful, more capable than we are. Or it could lead to a sense of connection, the realization that we are not isolated, that intelligence and curiosity and the drive to explore are not unique to humanity, but are properties that emerge wherever the conditions allow. Third, the practical implications. If we confirm that 3I Atlas or another object is artificial, the immediate question becomes, can we learn anything from it? Is it still functional, or is it a derelict? Does it contain information we can decode, or is it simply a piece of hardware with no accessible data? Can we communicate with it, or is it designed to operate autonomously without external input? Even if we cannot interact with the object directly, studying it would provide invaluable information about how another civilization approaches engineering, propulsion, material science, and mission design. We could learn new techniques, discover new physics, or identify technologies that we have not yet invented, but that are clearly possible because someone else has already built them. There is also the question of policy. If extraterrestrial technology is passing through our solar system, do we have protocols for how to respond? Do international bodies like the United Nations have frameworks for managing such a discovery? Do space agencies have plans for how to coordinate observations and data sharing? The answer largely is no. We are not prepared, not politically, not legally, not socially, for a confirmed detection of extraterrestrial technology. That lack of preparedness is something Loeb has been critical of. He has argued that science and society should be thinking about these questions now, before a discovery is made, so that we have structures in place to handle it responsibly. The Galileo project is part of that effort, an attempt to build the infrastructure needed to detect and study anomalous objects in a systematic, transparent, and scientifically rigorous way. But what if the bet is wrong? What if 5 years pass and no undisputable evidence emerges? Does that mean Loeb was mistaken, that 3I Atlas is just a comet and that we are alone after all? Not necessarily. Absence of evidence is not evidence of absence. If we do not find extraterrestrial technology within 5 years, it could mean that such technology is rare, that it does not pass through our solar system often, that our detection methods are not yet sensitive enough, or that we are not looking in the right places. It would not prove that extraterrestrial technology does not exist, only that we have not yet found it. And even if 3I Atlas turns out to be natural, even if every observation we make confirms that it is an unusual but ultimately conventional comet, the process of investigating it will have been valuable. We will have developed new techniques, asked new questions, and pushed the boundaries of what we can learn from distant observations. The scientific method works by testing hypotheses, and sometimes the most important thing you learn is which hypotheses do not hold up under scrutiny. The next chapter in this story is still being written. December 19th will provide critical data, but it will not be the end. Analysis takes time, debates take time, and the process of reaching scientific consensus takes time. We may not know the definitive answer about 3I Atlas for months or even years after the close approach observations are completed. Science does not move at the speed of headlines, it moves at the speed of careful, methodical evaluation of evidence. But the conversation has already shifted. The idea that interstellar objects might not all be natural, that some could be artifacts, is no longer dismissed out of hand. It is being discussed, debated, and investigated. Observing programs are being designed to look for the signatures that would distinguish natural from artificial. The next time an interstellar object is discovered, the first questions will not just be about its composition and trajectory, but also about whether it displays any of the anomalies we have been discussing with 3I Atlas. That is progress. That is how science advances. Not by clinging to old categories and refusing to consider new possibilities, but by following the data, testing hypotheses, and being willing to update our understanding when the evidence demands it. Loeb's bet is a statement of confidence, but it is also a call to action. It is a challenge to the scientific community to take these questions seriously, to devote resources and attention to the search for extraterrestrial artifacts, and to approach the problem with the same rigour and scepticism we apply to any other area of research. Whether the bet pays off or not, the fact that it was made signals a shift in how we think about our place in the universe, and what we might find when we look beyond our own solar system. 3I Atlas has given us a glimpse of what that future might look like. It has shown us that even one anomalous object can spark a global conversation, mobilise the scientific community, and challenge our assumptions about what is possible. Whether it is artificial or natural, whether it is unique or representative of a larger population of interstellar travellers, it has already changed the way we think about comets, about interstellar objects, and about the search for life beyond Earth. And that, perhaps, is the most important takeaway. We are at a moment in history where the tools exist to answer questions that previous generations could only speculate about. We have telescopes powerful enough to study interstellar visitors in detail. We have models sophisticated enough to predict their behaviour. We have the scientific framework to distinguish between natural and artificial processes. What we need now is the willingness to apply those tools without prejudice, to let the data guide us rather than our preconceptions, and to follow the evidence wherever it leads. December 19th is coming. The observations are planned, the data will be collected, and then we will see. We will see whether 3I Atlas is the beginning of a new era in astronomy, or whether it is a fascinating but ultimately conventional object that reminded us how much we still have to learn about the universe. Either way, the journey has been remarkable, and the questions we have been forced to ask have been worth asking. The search continues, the bet is on, and the universe, as always, holds more mysteries than we can imagine.